started it as induction proof, right? The reason why is because even though the question didn't say do it by induction, why not, right? Because induction is a method of proof, and as the question sort of set up, number one, you already know what you're trying to prove. That's a requisite for induction. Number two, you're dealing with integer values. Induction doesn't have to deal with integers, but it usually does, right? And number three, when you don't just know this, you actually know all the intervening values, right? So you can test things out. So that's why this question is sort of induction shaped, even if they don't say, prove it this way. So I just thought I'd draw some out, even though that doesn't necessarily contribute to my solution, because it helps me wrap my brain around what's happening. And then you can see I've just sort of started out my first three steps, right? So test it. First available value I just put as 3 because if you have anything less, you don't really have a polygon, right? Then I assume, now I have to prove. This is the fun part, right? Now when you look at this, how could you possibly work in your assumption into here? That's the question, right? Does anyone have any ideas? How would you go about doing it? This thing here, I could expand. It would end up with something that I would argue is no more complicated or no more simple than what I'm going to get in a second. So I'm going to leave it factorized for now. I think it really depends on this thing. It has to come from there somehow, okay? Because if I'm going to bring this in, right, I don't have it on the right-hand side. Even if I did have it on the right-hand side, what would it achieve for me to bring it back in, okay? So I think the key is to really understand, well, what happens when you go from, I'm just calling capital D the number of diagonals I've got, right? What happens when you go from 1, k, to the next one, k plus 1? Well, that's why it's actually useful to have this diagram, okay, or this set of diagrams. Because you can see a pattern, can't you? You can see a pattern. As you go from 1 to the next, what's changing in the number of diagonals? Well, it's getting more, but by how much? As you add in one vertex, as you add in a corner, right, you go from 0 to 2, right? So plus 2 diagonals, okay? As you move over from 4 to 5, you add how many diagonals? 3, right? Now, by the way, because the pattern is starting to come out, why is it that this number that we add on is so methodical, right? Well, 2 reasons. Number one, and you can sort of see it because I've got enough diagrams here, right? Number one, you've got more vertices to draw out diagonals to other places, right? Because if you think about it this way, I started here and I drew one, and then I drew another one, so I drew it twice, right? From 2 starting points, and then I was finished. There were no more diagonals I could draw. But when you go for this one, you're adding in an extra point that can go to more places, right? So you've got more starting points. But secondly, can you see the other thing that's growing as you go from here to here to here? Each corner, right? Not only are there more corners, but each corner sends out more diagonals, right? See here, I've got 1 diagonal per corner. There's just 1 coming out. Then you've got 2. Every corner has 2 diagonals. And then here, you've got 3, right? So that's why it's growing in this very sensible way, okay? So from here to here, plus 4. Now, what kind of series is this? Now, this series in here, that's arithmetic, right? Common difference of 1. But the actual series I'm interested in, D, is not arithmetic, is it? Like, it's just a series. It's not arithmetic, it's not geometric, it's just that, okay? So if I'm going to try and break apart that series, how would I do it? I can't use my normal rules or formulae for APs or for GPs, so what do I do? Well, I'm going to say, here's my left-hand side, okay? That the k plus 1th term, whatever it is, whatever rules it follows, right? It's going to be the previous, the previous k terms, right? That one, plus whatever the next one is, namely that. Okay, does that make sense? So for instance, if I was looking for the 100th term, it would be the first 99 terms, the first 100 terms. It'd be the first 99 plus the 100th, right? So that's my k and that's my k plus 1, right? Now this is useful because I'm trying to work in my assumption, right? So that's good, okay? I've got my d, k there. But in solving one problem, bringing it in, I've introduced another one. What is this thing? What is k plus 1? Remember, it's not an AP or a GP, right? So we can't use our ready-made rules for those. What else can I do? What else can I do? Observe the pattern, exactly right. Right? So I want to watch what's happening here, okay, and you can make some educated guesses. I'm going to go straight for the algebra, okay, because not only can I observe the pattern, I already have an algebraic expression for the pattern, okay. So I'm going to say, if I want to work out t of k plus 1, I'll put this off on the side, okay, t of k plus 1, okay. If I want to work out, say, the 100th term, a way of thinking about that is, well, if you take the first 100 terms, okay, and then you subtract all the ones except for the one you're interested in, right? So I should have done this, I think. That's what I wanted. Okay, can you see what I'm doing here? Okay, I'm taking the sum of every term up until this one, and then I'm taking away all the previous ones, all the ones I don't want, right? So what does this land on? What does it look like? Well, I know what all of these pieces are because I define them that way, right? Sorry, this is a D. I keep on thinking of sums. Okay, that make a little more sense? Okay, so d of k plus 1 is going to be k plus 1, k minus 2 on 2. Yep. And I know what this is already. That's k minus 3. Okay, off you go. What does it work out to? You tell me. I hope so. You have 2k minus 2. 2k minus 2. Because I've got here, what have I got? K squared minus 2k plus k minus 2 minus k squared minus 3k. Yeah? All on 2. That's just one fraction? Yes. Okay, so I've got k squared minus k. So this k squared will cancel with this k squared. Yeah. I've got minus k here plus 3k. So 2k minus 2. Yeah? And that's actually all over 2. So far, so good. So k minus 1. Okay. Now, does that make sense? Of course it makes sense, because k minus 1 is exactly what we're adding as we're going from term to term, right? 2, and then 3, and then 4. Okay? You see how it's growing in the same way? All right, now I can actually put this into place. So, here, what have I got? K minus 3. Right? Does it fit? Where do I want to go? Where do I want to go? This is going to be 2 on 2. Yes? So I've got k squared minus 3k plus 2k minus 2. All over 2. Yeah. K squared minus k minus 2. Does it check out? Ta-da! I should have left myself a line, but that's going to end up here, the factorized bit that I was after. Right? That's equal to, I can just fit it. Ta-da! What I was after. Okay? Now, yeah.
Are you allowed to make that assumption of the k plus 1 because that's what you're proving?
Yeah. This part here. Okay. So 2 things. I am assuming what d of k is. That's my inductive step, right? So I really should have said by assumption here.
Because if you substituted the tk plus 1 equals to dk plus 1 minus dk, doesn't that just cancel?
You mean from here?
No, if you substituted that top line into that.
This one?
Yeah.
Okay.
That's the phrase.
Yes, but no, because I'm not assuming that this is true, right? I'm actually working it out based on what kind of. So I should have said, as d is a what's the word I'm looking for? Is a progression. That's all I want, right? Because that's the definition of something which is progressing from term to term, right? So that's why it's not as circular as it looks. Okay? I think the hard part was here, that one, the step we're talking about, okay? Because it's not intuitive that like you'd go in that direction. And how else do you break apart this guy? That's the hard part, okay? Now you guys got lucky, there were no geometry induction questions for now. When your trial rolls around, they'll make another appearance because in your HSC, they'll make another appearance. Actually, if you go, when we get to the time when we get to look at real HSC exams, you'll see lots of geometry induction questions in there. Because geometry induction questions are hard, so that's why they make you do it. Okay? So anyway,